Oh, you got it, Jess? Okay. All right. Some folks wanted to retake the test. One person has emailed me already. If you want to retake the test because you want to use your notes for it, sure, yeah. Email me so I can get that info to you. Okay? Laura, before you leave today, you remember that your calculator is up here? It's still orange on the charging thing, so did you want to borrow mine during the class today? We're on chapter 6. What page is that there? 87. You are correct, sir. One of the things that I got to live through that you guys didn't is oops. What does that look like? A. That I got to live through that you guys did not is the moon landing, which was pretty spectacular. Let's see here. How do I get to that? Okay, why is that not sounding? Escape. Got sound here. Yep. Got sound here. What am I doing wrong? There we go.
Kilo has never been used. Is that correct? Stand by. Houston, while you're looking that up, you might recognize what I have in my hand as the handle for the contingency sample return. I just still happen to have a Inuit 6 iron on the bottom of it. In my left hand, I have a little white pellet that's familiar to millions of Americans. I'm going to drop it down. Unfortunately, the suit is so stiff I can't do it with two hands, but I'm going to try a little sand trap shot here. I got more dirt than ball this time. More dirt than ball. Here we go again. That looked like a slice to me, Al. There we go. Three the die. One more. Miles and miles and miles. Very good, Al. And answer Ed's question earlier there, Kilo was used for the window shot, Ed, so you ought to bring it back.
Okay. So that is the story that goes with the picture on page 87. Am I right there? Yeah. Page 87. So in 1971, Alan Shepard hit 2 golf balls on the moon. He swung 3 times. Now, he said he hit 2 golf balls on the moon. Anybody ever been golfing? And if you swing and the ball moves backwards a little bit, what's the truth? You got to count that as a stroke, right? Everybody agree with that? So he actually hit the golf ball. He hit 2 golf balls, but one of them he hit twice. Because I don't know if you noticed that very first swing that he took, the ball moved backwards because he missed it. Okay. Then it says, these balls experience constant gravitational acceleration during their flights. Were not affected by air resistance. The graph of the vertical velocity of the balls under constant acceleration is a line. So let's take out our notes. We have now dealt with gravity 3 times. I'm curious why that always comes up. Now, the first time that we dealt with it, we were talking about h as a function of t, and it was negative 4.9 t squared plus 20t, and that was the tennis ball in lesson 1. Do you remember that story? Where we had the tennis ball that was hit up into the air at, what was the speed? Anybody remember? It's right there in the problem. 20 meters per second up. Gravity was pulling it down at 9.8. So you notice that this number is half of gravity. The second time we dealt with gravity, we were talking about a rock, and we had negative 16 t squared plus 200 was our problem. If you remember that one, that was, we were on a cliff dropping a rock from how high? 200 feet. So these two are talking about, both of them are talking about Earth. This one, gravity is negative 32, which is, again, half as much as, or twice as much as negative 16. The first one, they were measuring things in meters. The second one, they were measuring things in feet. So 32 feet is 9.8 meters. Okay? Everybody clear on that? Do you see the difference between this one, where we were throwing the ball up, and here we were, cliff was 200 feet. Do you see how there's not a coefficient with that? I'm sorry, there's not a variable with the 200 feet? That's a height, okay? That's a vertical offset or a vertical shift. Everybody good with that? Okay. This one, it says it is a line. Well, let's take a look at these first two, and let's graph not the height, but let's graph the velocity. Okay, the velocity in this case starts out at 20, and it goes down until it gets to negative 20. Why? Because it leaves the ground 20 meters per second going up. When it gets to 20 meters per second going down, it stops because it hit the ground. Good. Everybody good with that? So that was this first one, where the intercept was 20, and the slope is negative 4.9. No, it's not. Negative 9.8. Okay? Then the next one, it started out at 0. We're talking just about the velocity. The velocity started at 0. Does everybody agree with that? It was going 0 when you dropped it. What's going to happen from there? It's going to keep on increasing in velocity down. In other words, keep on getting bigger and bigger negative. Everybody okay with that? So its velocity is also negative, and it stopped after 3.5 seconds. How come? Because it hit the ground. Okay? So the intercept was 0, and the slope is negative 32. Okay? This time, they give us the equation for the velocity. Page 87. It says the velocity as a function of time, but it doesn't give us the actual equation. What does it tell us about the velocity as a function of time in number 2? Plus 56, right? But what does it tell us? Negative 1.6 t. Right? It says each second it loses 1.6 meters per second. Now notice they don't give it as a negative, but do you see why it has to be negative? Because if it was positive, what would happen to the 56? It would get faster and faster and faster. So how would we graph this function? Well, we start up here at 56, right? And instead of going down at 9.8 or at 32, we're going to go down at how fast? 3.2. Now this is meters per second. Is the ball going to be in the air for more time or less time than either of the other two cases? More time? What are the two reasons it's going to be in the air for a longer time? It's got a bigger starting spot, right? It starts at 56, and gravity doesn't slow it down as much. Now, I showed it going out here to where it is 0. Does everybody agree 0 is where the ball stops going up? Did it hit the ground at that spot? No. When is it going to hit the ground? When the speed is... How fast? Close. The first one started out at 20, and it stopped when it got to negative 20. This one will start at 56, and it'll stop when it gets to negative 56. Everybody agree with that? So I think, well, let's do the math and figure out how long it takes to get to the top. What would we do? Well, we would take 56 divided by 3.2 17 seconds. I made a mistake here. Got to figure out where I made my mistake. I think. No, that's right. It's about 35 seconds till it hits the ground. No. Yeah, 35 seconds till it hits 0. I have to change this equation for the green line to negative 3.2. Nope, negative 0.8. I went the wrong direction. There we go. So, in order to have it go all the way, it gets to the top at 35 seconds. So I don't have my graph going high enough. Let's go to 1,000 meters. So if I have my graph going to 1,000 meters, we can get the journey of the whole ball, and I'll show you how it looks. So the red line shows the speed. Let's get the why can't I use B? Well, let's try C. Nope. What is it saying? Oh, I see. D. Oh, let's just delete this one here. There we go. Okay, so I'm going to start that. This number goes from 0 to 70, and now let's watch it go. So there's my ball going up in the air, coming back. Oops, I guess it doesn't go the other direction, does it? It only goes one way. Okay, so the ball starts, it goes up in the air for 35 seconds, it comes back down. Now, before you start on your lesson, I want to talk about, is this reasonable? In the actual video that we saw back here in our lesson, where the guy was swinging, I took the pictures, and they were, how a film goes picture, 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 picture. I measured how fast it took the swing to come down and hit the ball, and I figured out that it wasn't going 56 meters per second at the beginning. It was actually going about, I think, like 14. I can't remember what the exact speed was, but it was nowhere near 56 meters per second. Which leads us to say, well, how do you know it's not 56 meters per second? Fastest golf swing. Okay? Meters per second. There's an average. Here it says Tiger Woods on a par 5 registered a club speed of 129.2 miles per hour. 129 miles per hour, 2 meters per second is 57 meters per second. So this duffer on the moon with a 6-iron is supposedly able to hit almost as fast as Tiger Woods under ideal conditions with a driver on Earth, breathing air, two-handed, without a spacesuit. Got the picture? Okay. So as you go through this, it's make-believe. Do lesson 6B, number 3, and then we will go through the answers. Go. And while you do that, I'm going to take attendance. Nick, do you have a book? You can sit next to Jake here and work over there. Do you need paper? Because there's some right there. Do you need a pen? Here's a pen. Michael. You here? Michael?
No.
Marlena? Gavin? Janae? Felicia? Nicole? Eric?
Here.
Phil?
Yeah.
Grant? Connor? Faith? Laura? Madeline? Sarah? Jess? Lauren? Jake? And Sam. Okay.
I turn this to you right now.
Let it go.
This will be big. I don't know if I did it right or not. I'm not very confident.
Two of the ones I looked at.
Already wrong.
Well, you got right, but you didn't answer number one.
What?
What?
Oh, that's true.
What do you mean it's true? That's not one of the choices.
Yeah, I'm saying that, yeah, I didn't.
Oh, you
think I did.
Oh, okay.
I remember which one it was, though. I did, I just forgot to write it down. I don't know how. It's been a long few days.
And you got it right.
What?
And you got it right.
Oh, yes. Amazing.
I didn't say it was amazing.
Yeah, that means I got 1 point out of that test right.
No, I said the other one that I looked at you also got right. You guys doing okay? You aren't even on the right page there. Oh, you are. Okay. Part A.
For the first one, did you guys write, like, you have to, like, change the equations?
Okay, so what was the
Yeah, I
formula?
just like changed the equation because it doesn't.
Of T equals. Okay, so now take a T. How do you find V for it? Give me the words. Yeah, but what? How do you plug it in? You multiply it by what number? And then? Very good. That is how you go from.
What are the nickels so weak?
I don't know. I don't know.
Email your instructor so you can find it out.
Does that help you with B? Just if you want to, you can sit over here and then work with these guys. Or if you're fine working by yourself, that's okay too. That's fine. Madeline, you getting them?
Yeah.
Oh, you want me to work on it now?
I just don't want to be wrong, so I feel like if I write it down, it's going to be wrong anyway, so might as well just wait.
I don't want to be wrong. So when I was teaching high school, we would annually go to the ski hill, and most people didn't know how to ski. Everybody started on the bunny hill. When we were on the bus on the way back to school, there would be people who were absolutely pristine condition, and there were people who were like wetter than could be. Okay? Both of them would brag. The one group would brag, I never fell one time. The other group would brag, I made it down the double black diamond. We didn't have triple black diamonds. We only had double. It was Mankato. It's not that big there are no big hills around Mankato. Do you want to be somebody with a pristine snowsuit, or do you want to be all wet and have made it through the black diamonds? That's the question for you.
I already know how to ski, so.
Oh, yeah.
We're not talking about skiing, sister. We're talking about algebra. You aren't going to learn if you don't make mistakes.
The thing is, I just want to pass this class so I can my benefits and get
You will pass the class if you make mistakes. You will not pass the class if you don't try. So try.
Okay, Devin.
I feel so inspired right now. Start with a T. Start with a T. What do you do to T to get the first step? Multiply by negative 1.6, and you get negative 1.6t. Then what do you do to get your answer? Add 56, and you get negative 1.6t plus 56. Now we're going to start with v. How do we get back to t? Subtract 56. And what do we have? Oops, I'm sorry. I wrote it backwards. V minus 56. Then what do we do? And we have V minus 56 over negative 1.6.
Is that for question 2?
That is for question B. So, they say, what is the formula for T? I'm going to write it a different way. V negative 1 of T. That's what they mean. This is how we write inverse. Is start with V, subtract 56, and divide by negative 1.6. How did I do it? I did the steps in the reverse order. The only way I know the steps in the reverse order is do the steps in the right order first, and then go backwards to figure out how to get back to the starting spot. So V is negative 1.6t plus 56. T is V minus 56 over negative 1.6. Sam?
I just had a quick question about the equation. It's negative 1.6t plus 56. Since it's a does it not need to be t squared, or?
Okay. I'm going to go back up, and this is for Sam only. The rest of you can totally ignore what's going on. Up here, we were always talking about height.
Oh, got it.
That's why it was t squared. Height, t squared. Now we're talking about speed.
Got it.
Okay? So on the graph, when I showed you the Desmos, someplace, I showed you Desmos. In Desmos, this line here is the velocity. This line here is the, what do you call it? Height. And if you notice, to get the height to come out, if I want to get the height formula here, height as a function of t is negative 0.8 t squared plus 56t. Got it?
Yeah.
But we are not doing height in this case, we're doing speed. Okay. So, get back to work on C, see if you can get C. Oh, we did C. D. I want you to notice it is not 12. V is not 12. V is negative 12. How do you know it's negative 12? Because it's going down. So when you substituted that in, what did you get for T? Time? Eric?
42.5.
42.5 seconds. So at 42.5 seconds, it was going down at 12 meters per second. Everybody agree it's going to be after 35 seconds because that was where it hit the top. Is his answer reasonable, 42.5? Sure.
I did not get that. I got
Okay.
27.5.
So try it again. Negative 12.
That's it, never mind. Already figured out what I did wrong.
You had positive 12.
Yep,
And what did you say the answer was when it was positive 12?
27.5.
Does it make sense that your answer was as far before the top as his answer was after the top?
Yeah.
Okay. Yeah, you're both absolutely right. You guys okay, Menominee?
Yeah, we're good.
Number 4. 2. Importance events in the flight of the ball are when the ball reaches the highest point and it returns to the ground. What is the velocity of the ball when it reaches its highest point in flight? 0. Everybody agree? It's 0. So on our formula, we can use the formula for velocity, or to find time. V negative 1 of t is velocity minus 56 over negative 1.6. What number are we going to substitute in for v here?
0.
And what do we get for an answer?
35.
Everybody agree? 35? Substitute it in just to make sure. What does that tell you? It takes 35 seconds to go from ground level up to the top. Right? And then what happens? How long is it going to take to come back down? Another 35 seconds. Does everybody agree with that? So how long is it in the air? Total of 70 seconds. Everybody agree with that? Part B. At what time will it reach its highest point in the flight? 35 seconds. How long will it take? The ball will take as long coming down as it was going up. At what time will the ball return to the ground? Part C. Gavin? No idea? Help him out, Eric? Why is it 70?
It took 35 seconds to get out. It's going to take 35 seconds to get out.
Part D. Lauren, do you have any guesses as to what the speed will be just before it hits the ground? Obviously, when it hits the ground, it's going to be 0.
Honestly, not really.
Well, what speed did it leave the ground?
The 12.
That was a different part. Go back to the original formula. What speed did it leave the ground at, Nicole?
Was it 56?
56 meters per second, right? So what speed is it going to be when it goes back down? Negative 56, okay? It's an important thing to note. If you are ever one of those people that wants to go out and celebrate New Year's Eve or the victory over your opponent by shooting bullets up into the air, what do you have to be aware of?
The bullets come down.
At what speed? The exact same speed they go up. Do an internet search of people who get killed by bullets being shot straight into the air. There's a lot of them.
Yep. It's pretty sad.
Stuff that you don't. How does the ball's velocity at landing compare to its velocity at launch? Same speed, opposite direction. I want you to notice for part E something that's kind of crucial for physics. E. Same speed, opposite velocity. The speed was 56 meters per second. The velocity at the beginning was positive 56 meters per second, and at the end was negative 56 meters per second. We call velocity a vector quantity because it not only includes size, it includes direction. So when they ask the question, what velocity does it come down with? We would say negative 56. Okay? So let's go back to yesterday when we were talking about those satellites. We would say the vector quantity would have to be something like in direction 44 or in direction 13. I don't know how we would say it. Yes, Felicia.
I'm stretching.
Oh, watch out when you stretch, because if this was an auction, you would have just bought that flowered sofa. Kind of smells a little bit like cat urine, but
Is it comfortable though?
well, it was only $325, but it's really comfortable. So you're welcome. Everybody cool? Here we go. Now, a couple more things to consider. Here is Tiger. His speed was 57 meters per second in that direction. This Alan Shepard thing, is it ERD or ARD? Was 56 straight up. In other words, when he hit the golf ball, he would have needed to have a really, really, really high speed of the golf ball because they said it was 56 meters per second straight up. Well, a 6-iron doesn't hit it straight up. It hits it at about a 40-degree angle. I can't remember what it is. But the ball, he would have needed a much higher speed than that. If you look here at our graph, according to our graph, it would have gone almost 1,000 meters up into the air in order to be in the air for 70 seconds. Okay? How do I know this all is kind of made up stuff? here is the rest of the story that they don't talk about in okay, so if you zoom in here, oh, that's not right. If you zoom in here, you can see the spots that they are on the moon. Now, what's interesting about that is they are taking high quality pictures of the moon right now, and from Earth, you can see the leftover stuff from the space, from when they went to the moon. You can see those. I don't know if it's on Google Moon or not. I don't know where you can see them, but I just saw a picture a couple days ago of a different landing on the moon. But the reason why I love this story is, here is a picture of the spaceship as it was taking off. There's the flag that he was shooting the golf ball next to, okay? And you can see these tracks over here, okay? Now, just off to the side of that, as they were leaving, they took this picture right here. Hate that. Copy. Paint. Where's my paint program? Where'd it go? Menu. Insert. Cancel. Control V. Why is it not pasting? Don't save. Don't do that. Copy. Okay. Paint program. Start. I hate when they take programs out of our stuff so that we can no longer do stuff the way we used to do stuff. Okay, I'll try opening it in a different program then. They're going to be that way about it. I don't know which one to paste it into though. Maybe it'll be in this one. Ooh, that's an interesting program. That's not going to work. Oh, it's pasted in. Oh. Anybody know something I can paste it into? Photos. Let's try that. Nope. It's not going to let me do it there. Oh, whatever. I don't know if we will be able to see it or... Nah, that's not going to do it. I hate this computer. Right here in this crater right here, there's a stick that one of the astronauts threw, and right next to it is the actual ball that he said went miles and miles and miles. So it's like 28 meters is how far the ball flew, and he said it went miles and miles and miles. So when he got back and they looked at the pictures, here's the story that he told. While I was swinging the first time, the guy said, oh, that looked like a slice there. And so he said it was friendly banter with the other guy when he said it went miles and miles and miles, and it only went 42 meters. It was actually in the air for like 7 or 8 seconds. Can you imagine being in the air for 7 or 8 seconds and landing over by the corner of the hallway here? I mean, it was really, really close that it went. So there's a whole big internet story about it that I think is kind of cool that you would do well to read up about. Let's look at the rest of the lesson here. Consider the possibility that at the moment Alan Shepard hits the golf ball, Edgar Mitchell jumps upward with an initial velocity of 4.5. How long will he stay aloft? So you need a different formula than the one that we had before. Instead of 56, you're going to have 4.5. So find the answer if it's not 56, but 4.5. Okay, what'd you get? How long was he in the air? So what do you sub in for your formula to find out how long it takes to get him to the top? 0. And when you sub in 0, you're going to take negative 4.5 divided by negative 1.6, which gives you... What'd you get for an answer? Phil? You didn't do it yet. Sub in 0.
2.8.
Okay, that's how long it takes to get to the top. So how long is it in the air? How long is it in the air? 5.6 or 7 seconds, which would be really cool. Can you imagine playing basketball in a situation like that where you could jump up, look around, and then swat the ball, and it would, or volleyball. I was watching the Gophers women play volleyball the other day against Michigan State. Can you imagine if you were a volleyball player and you'd be able to jump up, look around, where should I send this ball? That'd be so cool. 5.6 seconds hang time. You'd have a lot of, you'd be able to like start reading a book while you were waiting for the ball. Yeah.
Would it be wrong if I substituted a negative 4.5 to begin with?
Oh, very good. If you put in negative 4.5 minus 4.5 divided by negative 1.6, he's using the idea that speed down equals speed up. In this case, if you subbed in 0, you would be saying top has velocity of 0, and then you had to double it to get how much time it was in the air. In both cases, you're working on an assumption. The assumption is, in my case, that it takes as long to get to the top as it does to get back down again. The assumption in your case is, when it hits the ground, it's going the exact same speed as when it left the ground. Finding intersections of lines. The movie scene features a car and a train moving parallel to each other. The scene calls for the car to accelerate and match the speed of the decelerating train. The train enters the movie scene traveling 75 meters per second and is decelerating by 3 meters per second. The car enters the movie scene at the same time, initially traveling 20 meters per second and accelerating at 5 meters per second. So they show the graph there in your book, and you can see how graphically it seems to make sense. Where did my picture go? How graphically it seems to make sense. So I did this with the college algebra class a few semesters ago, and one of the students said, "Doesn't happen, Kevin." I said, "What doesn't happen?" He said, "Do you know how fast 75 meters per second is? And a train does not decelerate that fast." And I said, "What are you, some kind of expert?" And he said, "Well, actually, I'm a train engineer." No, I never said that to him because I knew he was a train engineer. So I knew I should listen to him when he talked. So take out your internet searching device and find out, well, how the heck fast is 75 meters per second to begin with anyway? Give me for instance, 75 meters per second is Menominee. What do you get?
168 miles per hour.
Just 168 miles per hour. Well, that's not so bad. And then if you use that graph, just by looking at that graph, how long would it take if you're starting at 75 and you're decelerating by 3, how long would it take you to come to a complete stop? Anybody have any ideas?
Like almost a whole minute.
Yeah, I get 25 seconds, right? 75 divided by 3 is 25 seconds. Okay, so I did an internet search for a video of a train decelerating here. Here we go. Now this train was only going 167 miles an hour. Okay. That first one was, I don't know how fast it was going. That one was going 156. This one's going 168 miles per hour. Okay.
Real cost for a high-speed network, hundreds of billions of dollars for trains and tracks.
So you can see that those trains are trucking. Well, I've got here is a train that is going 80 feet per second, and it's going to take a minute for it to stop. It's feet per second, right? Yeah. So this train is braking about as fast as it can. So it takes a minute to stop. It's stopping at the rate of about 1 foot per second, a little bit over 1 foot per second. A foot is this far, a meter is this far, 3 meters is from me to my chair. So is it possible for it to decelerate at 3 meters per second? No, not a chance, okay? All right. Got one more video to show you. And that is, here's what they're trying to say is happening. So you got this car. I'm trying to catch up to the train. Okay, so that I can be the hero and jump from the car onto the train, and I like grab onto the bar, and I then go back and forth like that, and then I get my other hand up there, right here. Now, one of the things that I was amazed at, that's how deep that train is. Get up close to it. But I don't want to jump onto that thing. That is like mega huge. Okay, you get the picture. So, in Desmos here is the scene. Train, car. What is true at this spot right where they cross? And what time are they going the same speed? About 7 seconds. Page 90. Do 1 or 2 through 8. Oh, we'll do it after we come back from our break.
Every time it says break, we're just like adding.
Some people just need to get away from math temporarily.
I just need to get away from math forever.
Now, my question to you is, you were saying that you need to get this credit for your compensation.
Yeah.
Don't you also have a career goal in mind?
Yeah, to get done with this class.
And then when you get done, you will be an unemployed math student?
No, I don't know what I'm going to do, to be honest. I don't know if I'm going to do AGR, which is Active National Guard, or if I want to, keep going with school. Because I'm really just draining from this right now.
My niece is going into the Air Force in
Yeah, I can use this instead of paying to that.
Like, I'm
I got one.
to get.
I wanted to drop this class.
Oh, you're talking about, yeah. Yes, you can.
But if I drop this class, I'm not a full-time student, and I don't get my GI Bill. So I won't get my tuition reimbursement from my GI Bill if I drop this class.
And that's where I was going to go, is that my niece is going into the Air Force in December, and she's planning in the active service to be a geospatial something or another. So it seems to me like, since you do not mind the service, getting into a program that would be a career wouldn't be a bad idea.
It's something I really want to do, but I don't know.
You don't know what you want to be?
Yeah, it's either because go active duty and then wonder what it would have been like if I would have gotten what I want to be a gym teacher.
A what teacher?
A gym teacher. So then if I go active duty, then I'll have a contract. And it'll be like, okay, well then I'll always wonder if I wanted to do that. But if I go for that job, then it'll be like, okay, well I still have that part-time.
See, and there's advantages to both ways.
Yeah, you're running.
I don't think that there are any gym teacher jobs in the
Area.
Army.
Oh, no. And I didn't know that there were a lot in this area either.
Oh yeah, there's always need for gym teachers in every place.
Check the
Yeah.
front.
Yeah.
Whatever.
The advantage that you would have is, except for me, you get along really. No, I'm just kidding. You get along really well with people. You know, you have a way of not letting stuff get to you.
Oh yeah.
Which is really important, especially if you're teaching gym to high school students.
Oh yeah.
Especially to them, it would be just a pretty royal proportions.
then I'm like thinking about how like this past weekend went. And it was a long weekend.
Well, and that's, I can tell you this, you're learning a very important trait that you need to be as a teacher, and that is everybody has an opinion about how you should do stuff, and you can never please anybody.
Oh my god, so true.
So it's like the Army.
Yep, exactly.
And you know, and when I was younger, I used to like rebel against stuff like that. It's not.
There's no
It's not
no
worth
reason
it.
to, you know what I mean?
It's just, it is what it is, you know. And I go home at night and watch football, and it all goes away.
I'm just so used to getting yelled at all the time.
Yeah.
There's something wrong, even though it's the right way, but it's wrong. Like this weekend, we have 14 hours sustainment simulation where we were locked at top secret early and on computers for 14 hours straight.
Yeah.
That was my weekend.
Yeah.
What is this?
Yeah.
We had like our own we had our like own unit, smooth ever cleaned or whatever. And we were going against the enemy on like a map of Korea on the computer. We all died. Everybody died. It was just so stressful.
There's a speaker downstairs this morning who's talking about suicide. Be interesting to attend that. This semester I have 3 students for whom a relative committed suicide. It was very sad. For all 3 of them. One of them just dropped my class because she just couldn't like get her stuff together. I think, yeah, it was her brother. 2 brothers and a dad. And I had a friend whose friend committed suicide, and he was like, nobody will talk to me about it. He said, Seth, I'll talk to you about it, but you won't understand it after talking to me about it because it's ununderstandable. And an interesting statistic about it is they did a study of people who jumped off the Brooklyn Bridge to commit suicide, and about 1% of them lived. About 95% of the people who jumped off and lived regretted the decision the second that they jumped. So it is an interesting thing to think about. I think for folks your age, there's 2 problems with it. One of them is you can't understand the concept of death. By the time you get to be my age, you're like, yeah, death is an eventuality that is pretty close. You know, if I live another 20, 30 years, it's going to end. For young people, don't worry about death. It's never going to happen to me. I don't know if they teach you that in the service or not. Do they teach you about making sure you don't die? Keep your head down?
Oh, keep your head down, yeah.
Okay.
If they wanted you to keep your head down.
It depends whether if you're talking about like 3 to 5 second rushes when they're shooting at you or not. But they're just talking about not really what's in your head, what to do.
Mm-hmm.
It's more of just you're gonna get shot at.
Yeah, there's a bunch of interesting statistics out there concerning PTSD and studies like that. There was a famous quote in a movie that said the average lifespan of a second lieutenant in the during the Vietnam War was like, I don't know, 2 hours or something like that. It's not a true statistic because think how many second lieutenants there are in the United States Army. Quite a few. And there were only 50,000 deaths in the Vietnam War, 52,000 deaths in the Vietnam War. And you can't live without second lieutenants. You need them. So as soon as one died, they would need to replace that one. So it's just, the statistic doesn't make any sense. I don't know why the movie said that. I think there was a guy who made up the statistic to begin with. It's interesting stuff. Okay, now let's get to work on page 90. Go.
Go to the next page. No, this is page 9.
Get it done? Do you know what you're doing?
I was gonna do this in the next one. I have 2.5 hours. After I got done with that video. Yeah, it's like 3:40. Because I know it's one of the lower ranks. So it makes me do all the dumb stuff. So like, literally, I had to load up all the trucks by myself. So it's just only by yourself. Yeah. No one else has the same rank. There are other people that are new.
Oh.
So I don't feel like I do all the grunt work. So everybody just knows the rucksack, fire on the max. I like all because they have a teacher. I can't say anything. So the worst. Because it's sleeping outside, we didn't have a desk job. We don't really do anything. So like, all my mechanics are doing research and we just literally sleep on a computer. So I got my notes and I zero understanding. I told her, I go starting it where I was computers. What have you got? So basically, I'm just talking to it's stupid.
Okay. Let's look at them here. So I show the... Oh, you can't see that. So I went to Desmos, and I put in the two equation time for the train as a function of time, it's 75 minus 3t. How did that happen? Well, you look at the graph here. What is the intercept? 75, and what's happening to the speed? So it's negative 3t plus 75. How about the car? It's positive 5t plus 20. According to our work from yesterday, which form of the line is this? Look back at your notes. Intercept, slope form of the line. Maddie, email me so that I can send you the page that we took for notes on that, okay?
Sweet.
Because you're going to need that for later on. So both of those are in the intercept slope form of the line. Intercept at 20, intercept at 75. Now let's look at the graph of those two and see that if we graph the green line, it looks like this. If we graph the purple line, the car, it looks like this. Okay? So I'm going to run A. Now, should I start at negative 10? Does that make sense where to start for my time? Start at 0, right? And they're going to, the train is going to reach 0 at 75 or 25 seconds. So I think that's probably good enough for us to see what happens here. And I'm going to go, and you see that what is the role of that t? Well, you can see what happens when the t starts here. What is the role of the t? It helps us determine what the velocity is, right? So the t is a variable that helps us determine the velocity. That is the answer to question 4. What is the value of the t? T helps us determine the v, right? Because it says v as a function of t. Now, depending on whether it's car or train, you will have a certain relationship that takes place there. And those two relationships depend on the t. In other words, the t is the input, very good, of our function, and the v is the output. So the t just helps us determine what the velocity is. Number 5. Use the formulas that you developed to determine an equation with a variable t that is true when the train and the car have the same velocity. Finding a solution. Well, if you're talking about a graph, what is the solution? Very good. Here's the solution if they are a graph. Here's how you find the solution, where you have two equations in the intercept slope form, and what you do is you make them equal. So we've got our two formulas. The train was going 75, right? And what did we do to the time? Multiplied by -3. The car was going 20, right? And we multiplied by 5t. That's the formula. Number 6. This is important. What is the role of t in this situation? It's not really a thing that helps us determine velocity. It's a thing that helps us determine the solution, right? Because the equals is now saying these two things are going to be equal. It's not talking about some input and output machine. It's talking about one particular case. There's not multitudinous answers. There's only one answer. I see people looking at someplace other than the screen, and I start to wonder, okay, so algebra is so boring. You're going to watch a ladybug rather than algebra. Okay. That shows you what I'm up against. Okay. See if the person sitting next to you can solve this equation. I believe you can do it in 3 steps.
It's 55 over 8.
One side.
There are my 3 steps. Step 1, move the smaller number of t. Which one of these two t's is smaller? Okay, so move it. How do we move it to the other side? Add 3t to both sides. And we get 75 equals 8t plus 20. I said move bigger constant. I should have said move constant. So how are we going to move the constant that's next to the t? Subtract 20 from both sides. And we get 8t equals 55. Last step, divide. What are we going to divide by? And we get t equals 55/8, which is about 7 seconds. Okay? How do I know my answer is 7 seconds, not 7 miles per hour?
Is time.
Because it says t, right? And t is a time. How fast is the train going at this time? Well, if it starts at 75 and it subtracts 3 for each second, it's going to subtract over 7 seconds. It's going to subtract about 21 miles per hour, right? Or meters per second. I can't remember what it is. Meters per second. So how fast is it going to be going? About 54 meters per second. Oops, that's the second part. The first part is 7 seconds. It's going to be going 54 meters per second. How fast is the car going? 54 meters per second. Okay.
Oh.
Now, here's the problem. They are going the same speed at that time. If the camera is going to be catching something that is a worthwhile proposition, not only should they be going the same speed, but they should be at the same spot when they're going there, right? So the train has to mathematically be in a spot where if it slows down at that speed, and the car has to mathematically be in a spot where it speeds up at that speed, so that when they get into going the exact same speed, the camera is going to be able to videotape them, right? Or video them, or shoot them, or whatever. Got it? So even though this graph shows the speed, that doesn't help us if the distance is not going to be the same. Page 61, or 91, excuse me.
Ooh, so eager. Oh shit. So good.
To me, that's pretty significant. Now, was the driver at fault? He obviously, I mean, there's no way that you can see how fast that happened, right? You want to see it again? You don't?
Sure.
This endangered species is these antelope.
It is. It is very fresh for what happened this last weekend, but the difference is I don't hold this driver responsible because the self-driving car, you're not supposed to intervene. But even, I mean, it's obvious that driver had no chance because even if you would have been paying attention, you would have not noticed that bike came out of nowhere, right?
So whose fault is it? Is it the guy on the bike or is it the car? Because even if it was a person driving, they couldn't have stopped fast enough.
But who wears a black sweatshirt too in the middle of the night like that?
But part of the problem, yeah, those are all very extenuating circumstances. If you noticed what it said here, I think that was significant because what it says here is mounted on a self-driving Uber vehicle captured deadly crash with a pedestrian. The crash occurred on March 18th, 2018. The victim has been identified. Authorities said the vehicle was autonomous mode when he was behind the wheel. Uber has suspended testing of the self-driving. I didn't read what that said. Uber has suspended testing of self-driving vehicles in a number of states. So in my mind, Uber said they were responsible. If you were going to make sure this didn't happen again, what things would you program into your car, or what extra sensors would you add?
Do exist. And no matter what's beyond the horizon, your family can discover it together.
Oh, maybe you guys don't know. When they are out looking for crooks from a helicopter, what do they use?
Infrared.
Infrared. So if they had infrared sensors on the car, it would be able to pick up car engines, deer, right? Anything that gives off a heat signature. This lady that got run over by the car there. But then, who was it? Somebody said that she shouldn't have been wearing black. You know, all of those things kind of contributed to it. Why does Uber want to make sure they aren't involved in that? Figure it out. Can you imagine the liability insurance they would have to have? They need their cars to perform almost perfectly. Now, people are under the mistaken impression that they are better drivers than a self-driving car would be. Some people are, but the vast majority of them, I see you laughing, Marlena, the vast majority of them, at least the ones in front of me. Did I ever tell you the story? I was commuting from Mankato to Eau Claire when I first started working here, and I passed a lady who was reading a novel on her steering wheel. I mean, it was a thick book, and she was reading the novel while she was driving down the freeway. And I was like, oh, that's interesting.
Well, I'd be mad.
Okay, page 91. Give an example of a rule you could program into a self-driving car so that it would avoid colliding with any vehicle in front of it. Okay, so you're just talking about a car on a road and a vehicle is in front of it. How are you going to program your self-driving vehicle? Make sure your vehicle is driving slower than the vehicle in front of it, right? You will never have a crash if you're driving slower than the vehicle that's in front of you. Unless the vehicle in front of you is coming towards you, and then you've got other problems that you have to avoid. Okay? Page 91. Suppose the self-driving car is traveling along a single-lane road. It passes a landmark at time x equals 0, and its position is given by f of x equals 26.8x. There is a car ahead of the self-driving car that is traveling in the same direction. Its position is given by 22.4x plus 85 meters. Graph those two on your graphing device and answer questions 2 and 3. Go. I'll help you with graphing those things on your device. You might have to use a phone with that calculator. Laura, you know how to graph on that graphing calculator? Alicia, are you going to use your phone? Desmos? Okay. Desmos? Okay. You can use it on your computer since you've got your computer out. Okay, Maddie, are you going to use your phone or are you going to use your graphing calculator?
My graphing calculator.
Okay, y equals. All right, let's do the first equation. What does it say?
Those two. 8.
Right there. X. Okay, go to your second one.
For the two. Yeah, I was gonna say.
Okay, and now hit graph. Yep, there you go. Now let's see what it says.
Window range.
Air window range. Okay, quit. Window. I'm not sure what window range here means. Go to zoom and scroll down until you get to zoom fit. Enter. See if that corrects the problem. Okay, now, do those lines cross on your graph? So we're over here someplace. So they showed them not crossing in Desmos either. Where are they going to cross here?
Over that direction.
Okay, so hit window, And right now, your x maximum is 5. If you go down to x maximum being 50, let's see if that gets us in the range. Click graph, graph. Okay, you did okay on the x side, but now your y, it's going to be taller than where you are, right? So go back to window and let's change the y maximum. They say 197. Let's say 1,097. And then see if it. Okay, now they fit. Okay, so go to trace. And now that's exactly where they cross, right? Is it? I don't know. So let's change our. You're going to have to write this down so we can see. So we're going to zoom onto that spot where they're going to trace. So x is 22 and y is 603. So now let's go back to window and let's change it so that our x, get around that, so say 20. Yeah, x minimum is 20 and x maximum, say 25. That should do it, right? Y minimum, say 590, and then maximum, say 610. Now I'll do the window or the graph. Ooh, we missed it. Okay, it's lower than we were, right? Change y to, let's say 550 to 600. Nope. That was the minimum. Yeah, you don't want that. That's okay. You gotta wait till it's done. Now go there.
This was 590.
No, 550. We said 550. Change it to there, and it's okay if it's 610. Let's see if they both. Oops. So you see how we were a little bit. We got to go back a little bit and lower. So let's say 15 to 20 is our x. And then y is, say, 500 to 550. Ooh. Okay, now do that trace and see where you end up. Now, so I just spent a few minutes helping somebody with the graphing calculator part of it. And it took us quite a while to get to that spot. Let's see how we can do that quickly in Desmos. So the first thing that I do, I'm going to turn all of this stuff off so that we're back to just... Where are those red dots coming from? Oh, there must be one more thing on my... There they are. Okay. So, I'm going to go back here to Desmos, and I'm going to graph those two functions. F of x is the train. G of x is the car. One advantage that I see... Oh, Laura, your calculator is still charging. So, one of those advantages I see is... I've got color right away. Does anybody have a color graphing calculator? Nobody except me, huh?
I'm not rich, Kevin.
Well, and that's one of the things that is very frustrating to me. How much does a graphing calculator cost, a color one? Say about $120. How much did your phone cost? About $120, right? When was your phone made? Okay, $1,000, whatever. My point is, your phone was made relatively recently. That graphing calculator was invented like in 1990. Can you imagine carrying around a phone that was invented in 1990? Have you watched movies from 1990 where they had high-tech phones? Okay. First of all, it was like your shoe, and it had an antenna out the top, and you would hold it like this. You did not carry it in your pocket. Okay. I don't know where you would carry it, but they were huge back in those days. Your graphing calculator is the exact same technology. It has not changed. If you want to use your graphing calculator, I'm okay with that. To me, Desmos is the way to go. So I graphed it in Desmos, and automatically the window comes up not too shabby. How do I make the window work? Well, I can see that if I graphed from 0 to 50, that would be seconds. And I graphed from 0 to 1,000, that would be feet, or is it meters? I forget. My graph fits on there. But the nice thing is, if I click on either of the two equations, I get the coordinates of the intersection. That automatically comes up. Also, what automatically comes up when you click on a line is what the point where the y-intercept is, and the x-intercept both. So, what does this tell us? That after 19.318 seconds, these two cars are going to collide. Your self-driving car needs to prevent that from happening. You're coming up behind the truck. You are at fault if you run into the truck. You need to correct your speed. So on page 93, it gives us a formula. Number 5. Does the car ever catch up to the truck? Yes. What time? 19 seconds. What position? 517 meters. Number 7, I think your book is wrong, but I'm not sure if they changed that in your book or not. For number 7, your formula should say 26.8 x minus 0.1 x squared. 26.8 x. So enter that into your computer or your graphing device and see what happens. Number 7. So I'm going to get rid of my first equation, and I'm going to change it to 26.8 x minus 0.1 x squared. Do I collide in the first 30 seconds?
What's the other one that we put down there?
Yeah, 20. Oh, it's this one, right? It's the truck. 22.4 x. So if they don't collide in the first 30 seconds, what leads you to believe that they won't ever collide, according to what you look at on your graph? What's happening after about 30 seconds? They were getting closer and closer together, and then now what's happening after 30 seconds? The two lines are getting farther and farther apart, right? So do they collide in the first 30 seconds? Explain how you can tell by examining the graph. First of all, the lines don't cross. Eric, do you have the modified car on there?
With the negative 0.01
Yeah.
x squared? Yes.
Did you turn off your original car one?
Yes, I got rid of the original one.
Now modify your y-axis to go up to whatever that lowest number is there. I can't see what that number is. But go from 0 up to still way too much. There you go. Oops. There. Okay? So they don't collide in the first 30 seconds. Page 93. If the car is programmed to obey the modified position function f, how close does the car get to the truck? Let's draw the picture here. Here is the car. Here is the truck. Now, I would maintain there are two ways to describe how close together they get. What are the two ways? Actually, I can think of three ways. How close they are time-wise. So at the same time, how close they are. And how close they are at the same distance. And then there's one more way, and that is how close they are perpendicularly. So when it says how close they are, I don't know what they mean. Because you can say, how far do you live from school? Well, you can say 20 minutes, or you can say 15 miles, right? So what do they mean by how far? How close do they get? Okay? It appears to me, if we look at it here, let's look at the graph. I'm going to zoom in on the graph to about, say, around between 20 and 30 seconds. Between 20 and 30 seconds, and say between 500 and 700 feet. Oops. Okay, so if I'm going to say how close do they get, let's say the time is 22 seconds. So at 22 seconds, how far apart are they? What math would you do for 22 seconds? 589 minus 552. How far apart is that? 37, right? 37 meters apart. Is that as close as they get? I'm not real sure. Let's go a little bit farther here. (622), 585. What's the distance apart they are there? About 37. So it appears as though they stay around 37 meters apart. That's about as close as they get distance-wise. How would we find the time-wise? Well, we would make the y be, let's say, 550. So at 550, how far apart are they? About 1.5 seconds. So think about it that way, is that you're on the side of the road, and the first one goes past you, you click a stopwatch. Then the second one goes by you, you click a stopwatch. What's the difference between those two numbers? About 1.5 seconds, okay? I don't know, do they get any closer together than that, let's say 600. So at 600, how far apart are they? 22.99, 24.65, about 1.5 seconds again. So it's difficult for us to mathematically figure that out. Is there a branch of mathematics that would help us figure that out? I wonder if there is. Yeah, we call it calculus. Okay? Calculus would be able to help us figure out how we get those two the closest together. One of the rules that's true is that wherever that point is, it's going to be parallel to the speed of the car. So we're going to have to make a formula that has, instead of being, I forgot what the truck was, 22.8.4 plus 85x, we would have to have it be something like k of x equals 22.4x plus 82. Well, no, too small. 40, let's say. A little bit bigger than 40. So anyway, you can see that as you get closer and closer together, you get that spot where it's going to satisfy the equation only one time. That's not where it wants us to go. Page 93. If the self-driving car continues for a few minutes on the course, determined by the modified function, we're going to change our graph so that the y or the x goes from 0, let's say, to 200. Well, when the graph goes to 200 and the distance, let's go from 0 to, say, 2,000 meters, you can see what happens to the speed of your car. What does your self-driving car do? It keeps on slowing down, slowing down, slowing down until it stops, and then what does it do? Starts backing up, right? Is that a good thing for you to do on the road? No. So you're going to want to modify your computer program slightly so that once the crash is avoided, you go no slower than the car that's in front of you, so that you don't crash. Page 95. Solving systems of equations graphically. So we showed you those two lines crossing in that previous problem. We're going to talk about phones, and they talk about the IQ phone. Makes and sells more and more smartphones. How would you expect the company's revenues and costs to change? So we're going to make these into linear functions, and we're going to see, you're going to be in charge of figuring out how to make money at your cell phone company. Anybody buy a new cell phone recently? Anybody know how much the new iPhone costs?
Too much.
Thank you. That was two people saying the exact same thing. I was amazed. Aren't they like $2,000? $2,300, something like that. If you wanted one of the fancier iPhones, I paid, I think $600 for my phone like a year ago. I don't think it's worth $600. I mean, I've got computers that cost less than that stupid phone costs. I don't know. Anybody pay $600 for their phone? Did you?
I'd buy mine outright. I'd buy an older version.
How much was it?
I bought an older version because I was inebriated while kayaking on the lake, and so I bought an iPhone 6 brand new for $200.
So a couple years ago, we were up fishing on Red Cedar Lake, and there was this guy in the lake, and the water was really cold. It was like 50-some degrees, and so we went over next to him just to see if we could help him out, and he said, yeah, I saved my $6 fishing lure, and all it cost me was my $400 phone. He had jumped into the lake to save his lure, forgotten that he had his phone in his pocket. I don't know if he was inebriated or not, though. That is a good question. Page. What page is this in our book? 95. Let's look at these two formulas. And I'm going to write them not as formulas, but as functions. Cost as a function of x equals 12,000 plus 30x. Revenue as a function of x equals 150x. So, let's talk about what these two formulas are telling us. The cost to make a phone is how much money? That's how much revenue you get when you sell a phone. In other words, to sell the phone, you get $150 for each phone you sell. But to make them, how much does it say it costs to make a phone? According to this model. $30. What's the $12,000? That's how much it costs even if you make 0 phones. Okay, that's how much it costs for your factory or for your heat or for your insurance and all those kinds of things. Now, it doesn't include the raw materials because that's part of the $30 that the revenue is. So we have two equations, and it says we are going to solve these graphically. We call this a system of equations. Let's graph this system and solve it. How do we graph the first equation? Start at $12,000. $12,000. And increase so that at some point, let's say this is 100 phones. So after 100 phones, it'll be up to 100 times 30.
15,000.
It'll be up to 15,000. The revenue graph starts at, what's its y-intercept? 0, right? After 100 phones, where will we be?
15,000.
No, I did not remember that was the answer. It was just a number that I guessed. I said 100. But as you can see, that is our solution. So at 100 phones, how much money will we have made?
0.
15. Well, yeah, we would have sold $15,000 worth of phones. Before that point, we would have lost money. After that point, we would have made money because you see the difference between those two. We'll start there tomorrow.
Yeah, it's like an extra fucking 8 mile drive.
Where do you reside?
Bright and early.
North of Menominee.
It's still not totally charged. Do you have a charger cable? Here, you can use mine.